What's up, guys? Welcome to another video brought to you by The Simple Engineer. Today we're going to be delving into a really cool algorithm problem that's known as stable matching. So within this video, as you can see, we're going to be talking about the background, explaining some of the definitions that are used within stable matching across many textbooks and videos. We'll go into the applications, actually see where this stuff is being used in real life, how it's useful today. I'll walk you guys through a step-by-step example, walking through how stable matching works on paper, and then we'll go ahead and take that example, we'll look at the pseudocode, and then we'll throw it into some Python and write it up from scratch. So without further ado, let's get started. So essentially what we want to do is dive into the definition, some of the background for what this problem actually entails. So the algorithm is commonly known as the stable marriage problem, or the GS algorithm, which is Gayle Shapley, the authors of the original algorithm. And the reason that it's called the stable marriage problem is because it's typically metaphorically represented by two sets of men and women in which you find the most stable preferenced combination between the proposals of men to women in two sets. So the problem statement defines the problem as finding a stable matching between two equally sized sets of elements given an ordering of preferences for each element. So essentially what we have is we would have, let's say we have some men, we have man, let's see here, we have man 1, man 2, and man 3. And this would represent a set of elements of men, and then each of these guys would have a preference of the associated women. So we would have women 1, women 2, and woman 3, and that would be a vector of preferenced men in an ordered ranking. So let's say man 1 prefers woman 2, woman 1, woman 3, we got woman 3, woman 1, woman 2, etc. So what we're saying is that given two sets, i.e. this is one set and this is another set, two sets of n elements in each set, so we have 3 elements in the first set and 3 elements in the second set, with an ordering list of preferences for each element in the set, i.e. the list of preferences here would be the women, the list of preferences here would be the men, then we are guaranteed to find a stable match, or in this case, a stable marriage between the two elements. So if we have n men and n women, where each person has ranked all the members of the opposite sex in order of preference, which we've done here, then marry the men and the men and women will get married together, such that there are no two people of the opposite sex who would both rather have each other than their current partners. So there are no such pairs of people. When there are no such pairs of people that follow this condition, then the set is deemed to be stable. So let's go ahead and draw a picture to better represent what this means. So we would have, say we would have 3 couples. We have a man and a woman, and we have another man and a woman, and we have another man and a woman. So what we're saying in the use case of stability, if we're talking about stability, then that means that, this would be man 1 and say woman 3, man 3, woman 2, and say man 2, woman 1. So this is the end result of, say, we did some matching, and this is what the result came out to be. We're saying that this edge case would be stable if these people are happy together, these people are happy together, and these people are happy together. Now, we could also have stability as long as the element in the opposing set does not reciprocate the same feelings. So if this man was with this person, but he was not happy, he had feelings for woman two, then this is still stable because she's not reciprocating the emotions to man one. So she's still happy with man three, and let's just say man two is still happy with man one. So that would be stable. There are not two people of the opposite sex that prefer each other over who they are currently matched with. Now, contrary, if she did reciprocate feelings, say woman two actually liked man one over man three as well, then this would be unstable. That would not work. But we can even have, another arrow. Say woman two actually prefers man two over here. Well, this is still stable because man two does not prefer woman two over his current woman. In fact, he could also prefer woman three, but woman three does not prefer man two over man one. So you see, there is no reciprocation. So in order for instability to occur, then we would need the idea of reciprocation, in which the two elements prefer each other over their current partners. So as long as that never happens, as long as there is never reciprocation for likeness of two members of the opposite sex over their current situation, then we have a stable marriage or a stable match. And that's a little background problem statement for the problem at hand. So next we'll look at some examples and use cases step by step for how this algorithm actually works in practice. So the next little tidbit that I want to bring up is some of the real life examples and applications of stable matching in real life. So I have some things listed here. They're just some examples of things that I've read about through different research papers for the actual applications of stable matching. And the first one that's actually really popular is something known as the NRMP. And the NRMP is the National Residency Matching Program, which is a nonprofit organization brought to you for doctors or medical students that are looking to seek residency with their preferred hospital and get matched up with the best possible hospital. So I'm going to put this link in the description, but I really encourage you to go to the nrmp.org website, and they actually have a PDF, which will be linked in the description, where they go through how their algorithm works. So the way that this works is students actually essentially pick their top medical hospitals that they want to work at and become a doctor at throughout their residency. However, the doctor wants to make sure that they get the best student possible as well. So, like I said, the two sets need to have n equal elements. So, the way it works, say that there are 10 students in 5 hospitals. In some theoretical example, each hospital would have essentially 2 open spots. So that would cover the 10. So that would create n-sized elements between the two sets. So the hospital would essentially put in their preference and the students would put in their preference. So this is kind of a cool example because it's a little bit non-traditional in the sense that, you have your students and they put in maybe just one of their preferred hospitals, and kind of walks through the process in which the chooser, the student, gets the best possible outcome, and there's this stable matching for resident to hospital and hospital to resident. So I encourage you to look at this example. It's very well known and pretty cool. Some other examples, they're a little bit silly, but Sorority Rush. So, there are actually cases in which sororities have used the stable matching algorithm to pick candidates in certain colleges to join their sorority for the best candidate. So the sororities pick who they like the best, and then the person picks which sorority they want to go into, and the stable matching algorithm does the rest of the work. There was also a really cool case where students in New York City put their preferences of high schools, and high schools looked at a bunch of different variables to pick the students that they wanted the best, and that was another use case. The last one that I'm going to mention is networking. So when you go to a website, stable matching has actually been used where, the user will definitely want the fastest response times and the quickest rate, proximity, and whatnot. And the network wants to spend the least, deliver content from a specific server that will not cost as much, that will deliver content fast. So it's this kind of a pairwise mapping between the user and the different sets of servers to display content fastest and cheapest way possible. So these are some common real life examples for stable matching, and I just wanted you to know that this is a useful algorithm that's being used in the industry today. So we're going to jump into an example. I'll walk you through step by step how this algorithm actually works. Okay, so the thing that most of you have probably been waiting for is an actual step-by-step example for how this works. So what we're going to do is we're going to use the example of a high school dance. And in this dance, there's going to be some guys, and they want to ask a girl to join them in, their prom, their high school prom. And they're going to have a preference list of people that they want to go with, and so are the women. So in this example, the men are going to ask the women to join them in prom. So let's go ahead and say that we have, we're going to have 4 guys. We're going to have Brian, Josh, Blake. So these are the ranked preference of people that the women and the men prefer. So the way that this works, so the algorithm, one thing to note that you need to know is the algorithm is 100% guaranteed to find stability. So you want to know that. I mean, this is a good algorithm. It will 100% of the time find stability. And there's a proof. There's a proof on this. It's not that difficult. I'm not going to go through it in this video, but that's one thing to keep in mind. So the way that this works is you start with the person that's going to start first. This is something that matters. The person that starts or proposes to or asks the opposing party is the one that's actually guaranteed to get the better outcome. And we'll see that. The person that's actually getting asked to, or the proposee, is going to get the worst outcome for them from their perspective of the woman. So it's good to note that you actually want to be the one to choose first. You want to be the one to propose to, and you'll get the best outcome possible. So in this case, you start from the most liked, and you go to the least liked. Okay, so this is people that he likes the most, and this is people that he likes the least. So we're going to start with Liz. And the way that this works is we start with Lizzie, and we go over to Lizzie, and her top pick is actually Ryan. And Lizzie hasn't been asked to go to the dance yet, so she tentatively engages. Now, for this to break off, the only thing she can do, she can never be single. The person that's being asked to go to the dance or being proposed to can never ever be single again. She can only trade up to somebody that she prefers more. So Ryan asks Lizzie. Lizzie has not yet been proposed to, so they get tentatively engaged. So Ryan and Lizzie are now tentatively engaged. So now we go down the list to Josh. And Josh proposes to go to the dance with Sarah. Well, we go over to Sarah, and her top pick, I mean, Josh is her last preference. but she has not been asked to go to the dance yet. So she tentatively accepts and says, okay, I'm going to go to the dance with Josh. Okay, so now they're tentatively together to go to the dance. Tentatively. It could change, though. So now Blake comes along and he says, oh, well, I like Sarah. That's my top pick, right? So we go over to Sarah. Well, she's already going to the dance with Josh. But Sarah says, well, Blake, he was my second pick, so I would much rather go with Blake. So Blake and Sarah get tentatively put together and they go to the dance. Well, Josh is now, he's on his own. She dumps Josh, and now we need to go back to Josh. Josh is like, well, I don't have anybody to go to the dance with now. So Josh says, well, I'm going to go look at Lizzie. So he wants to go ask Lizzie. Well, Lizzie is already with Ryan. So Lizzie says, well, I like Ryan way better than Josh. Josh was my third pick here. So I'm not going to go with Josh. So now Lizzie's out of the question. So Josh is like, well, crap. Now I need to go to my third pick, which is Daniela. So I'm going to go to ask Daniela. Josh goes and he asks Daniela. And Josh is actually her second pick, but she has not been asked yet to go to the dance. So they tentatively accept each other's invitation for the dance, and now they're tentatively together. So now Blake, he's already with Sarah, so we go over to Connor. Connor's first pick is Lizzie. So we go look at Lizzie. Well, she's already happy with Ryan. I mean, this is not going to change because they both had their first preference pick, and they're good to go. So that's not possible. So now Connor says, well, I want to go ask Sarah. So he goes to Sarah. Well, Sarah, she's going with Blake. And Blake is actually of higher preference than Connor. So Sarah's out of the question. So Connor's like, well, I guess I have to ask Zoe because, Zoe's my next pick. So we look at Zoe, and she has not been asked yet to go to the dance. So Connor asks Zoe, and Connor's actually her number one pick. So they tentatively accept. So what you notice now, the termination of this algorithm is when all men or all people asking or proposing to are completed, right? They're no longer tentative. So as you can see, Ryan is going to the dance with Lizzie, and Josh is going to the dance with Daniela, and Blake is going to the dance with Sarah, and finally Zoe is going to the dance with Connor. So now that there are no more free men, the algorithm would now terminate at this case. So what we've done here is we have found a stable matching between Ryan and Lizzie, Josh and Daniela, Sarah and Blake, and finally Connor and Zoe. So what this says is there is no other, this is a guaranteed stable match into which there is no two people of the opposite sex that prefer each other over their current matched situation for the dance. This is the best stable match possible. There's one thing to note. If I were to, say, start from the bottom of the list with Connor and work my way up to Ryan, I would actually get the exact same outcome. It does not matter what order that you do this algorithm if you're starting with one set. The order in which you do a set does not affect the outcome of the algorithm. However, like I said, if you're in this set where you're asking the question to the other set, then this set right here is guaranteed to have the most optimal outcome for them. And the other set, in this case the women, is guaranteed to have their essentially worst outcome that they would prefer most of the time. So keep that in mind. It is better to be the one proposing than the one to be proposed to. So that's an example. The next thing that we're going to look at is an actual coding implementation using Python, and we'll delve into it. So let's look at that. Okay, so Now we're going to dive into the actual implementation of the stable matching algorithm. Now, this is by no means the most efficient way possible. It's not the best way possible, but I'm hoping to at least take some of the content that we've learned and incorporate it into some useful code. So, a couple things to note. I will be referencing the stable marriage problem Wikipedia page. So if you go ahead and Google that, or I'll put the link in the description, there is some pseudocode for this algorithm. So if we can just walk through that really quick, essentially we initialize all the men and women to be free, and while there's still a free man who needs to propose to a woman, then we go ahead and we say, okay, we're going to take his top preference, right? And if she's free, then they're going to become tentatively engaged. However, if she's not free, but she likes this guy more than the current guy that she's with, then that current guy becomes free, and then this new guy that comes over, they get engaged. And if she doesn't like this new guy more, then she stays with the guy that she's currently with, and then that guy goes and he goes to the second loop. And this will continue until termination, and termination occurs when all men are successfully proposed to and the tentative engagement is finalized. So let's go ahead and start implementing this. So a couple things that I want to do is we're going to be going off the previous example that I wrote and comparing the solutions for that. So I'm going to create a dictionary, and this is going to be the preferred rankings for the men. And if you can remember, we had Ryan, and he preferred Lizzie, Sarah, and I'll just go ahead and type these in for you guys. Okay, so these are the exact same people of preference that were from the previous example. Now I'm going to create a data structure called tentative engagements, and this is going to be a list, and this is going to essentially contain all of the people that are tentatively engaged but may change before the algorithm terminates. So here we can just say keeps track of the people that may end up together. That's essentially what that is. And then, of course, we want to keep track of the free men, or the men that have not asked somebody to go to the dance yet, since we're doing a dance in this case. So here, this is going to be men who still need to propose and get accepted to go to the dance. Okay, so now let's go ahead and do a little bit of initialization. So I'm going to create a function, and I'm just going to call it init freeman. And what this is going to do is essentially it's just going to go through for each man in the preferred rankings of men. We're going to look at each key, and we're just going to append each of these men to the free man list. So here we're just going through each of the keys: Ryan, Josh, Blake, and Connor. We're taking those keys and we're pushing it into the list of men that are free. So this entire list is what deems whether or not our algorithm is going to get terminated or not. So with that being said, let's go ahead and begin the stable matching code. So we'll go ahead and create a function. We'll call it stable matching. And what this is going to do is it's going to look for the termination condition. So we're going to say while the length of the free men list is greater than 0, let's go ahead and take each man in the free man list and begin the matching algorithm. So we'll say begin matching, and we'll put in man. So what we need to do is create a function, and we'll call it begin matching. So far we've initialized the men that are free. They have not yet asked anybody to go to the dance, and they're in their own list. And this algorithm will continuously repeat until the free man list is empty. So while the list is not empty, we'll go through and take each man and begin the matching algorithm. So we'll go ahead and create the begin matching function, which will be the basis of the algorithm. So far we've covered essentially these first couple pieces here. So we'll say begin matching. It will take in the man that we're dealing with, and we'll say, okay, right now we are currently dealing with, just for the sake of testing, we know that we are dealing with this man in the terminal. And we'll say, okay, for each woman in preferred rankings men for this man. So we'll say for each woman that this man prefers. So in the first case, if Ryan, each woman would loop through each of these string elements of this list. So for each woman that he prefers, then we'll go ahead and we'll get a Boolean to see whether or not she's taken. So the way that we'll do this is a little Pythonic expression that will say taken match, and we'll say couple for couple in tentative engagements if woman in couple. So what this is saying is we will get a tuple of the woman and her associated match. If it exists, then it will be a tuple of the man and woman in the tentative engagements list. Otherwise, it will just return an empty list, meaning that she is single. So we'll say if the length of the taken match is equal to 0, then we'll go ahead and we'll say, okay, she's single, so that means that she can immediately get tentatively engaged with whoever asked her to. So we'll go ahead and we'll say, okay, tentative engagements dot append, and we'll go ahead and put the man and the woman in tentative engagements. So now we want to make sure that the guy that just asked this woman to the dance gets removed from the free men list because he's no longer a free man. So we'll say freeman.remove man. So just for the sake of sanity, we can say, okay, %s is no longer a free man and is now tentatively engaged to %s. So man and woman. So this guy has now married her, so he's no longer free and they've been engaged. Okay, so because we're looping through every woman in his preferred ranking, but he's already been engaged, we can go ahead and break this off. Now we need to satisfy the next condition. So the next condition essentially states, we just satisfied this. She's free, they became engaged. But now we need to say, oh, she's not free. So we need to check the preference ranking of the new guy and the guy that she's currently with to see whether or not she wants to step up her game to a more preferred human or guy. So we'll say elif if the length of taken match is greater than 0. So in this case, she is not single. Then we'll go ahead and say, uh-oh, %s is taken already, where %s is the woman. And we'll go ahead, and this is not the most fancy way of doing this, but just to kind of state who we're dealing with, we'll say, okay, the current guy is equal to preferred rankings of the woman for the current woman dot index, and we'll say taken match sub 0 sub 0. Okay, so what does this mean? What this means is the current guy is equal to the person that she is currently engaged to, because taken match is essentially a tuple of the woman and the man, and we are getting the order at which he is ranked for this woman. So in this case, say the woman is Daniela and she's currently with Josh, then this index function would return a 1 because this is indexed at 0. So Ryan would be 0, 1, 2, 3, and we're going to compare the indices of each of the men, the man that wants to be with her and the man that's currently with her. So we'll say potential guy equals preferred rankings women for the woman, and we'll get the index of the man. So now we can do a comparison to see who's better. So if the current guy is less than, which would be better than the potential guy, then we can just say, oh, well, she is satisfied with whatever guy she's with, where that guy is going to be taken match sub-zero, sub-zero. So just really quick side note, the reason that we do sub-zero, sub-zero is because this returns a list of lists, right? Or this returns a list of lists. So to get the first list of 1, we do sub-zero, and the first element in that list is a man, so we do sub-zero again. Okay, so else we can say, oh, well, %s is better than %s, where this is equivalent to the new guy is better than the old guy. Okay, and with that we can say, okay, well, now we're going to make the old guy free again, and then tentatively engage or tentatively accept dance between %s and %s, where this is going to be the taken match sub-zero, sub-zero. So this is the old guy, and now the man and the woman are going to the dance together. Okay, so now we can say the new guy is engaged, which would make us remove him from the free min list. So we will say free min.remove man, because he's no longer free. He just engaged the current woman. And then we'll say, okay, well, now the old guy is now single. So if the old guy's single, then we're going to push him back to the free man list. So we'll say freeman.append, and we'll say taken match sub-zero, sub-zero. And then we will say, okay, well, let's update the fiance of, or not the fiance, update the student for the dance of the woman. And this is going to just be taken match sub-zero, sub-zero equals man. So this is a little pass by reference trick where we'll update the value of the tentative engagement man slot to be the new man now. And then we'll just go ahead and break out of this so we don't continue looping. So that should essentially be it. But now let's go ahead and call our functions. So in our main, we'll just go ahead and say init free man, init free min, and that will initialize the min to all be free. And then we'll go ahead and initialize the stable matching algorithm. So this will find all the stable matches, and then we'll go ahead and say complete list of dance acceptances, and this will be just the tentative engagements list. Okay, so let's go ahead and try and run this and see if we get the same results as last time. So over here in my terminal, go ahead and python stable.py, and looks like we have quick error. So let's go ahead and look at this. Free man is not defined. Man. Where we got the free min. Okay. Cool. All right, so we'll go ahead and rerun this. And as you can see, we start with Blake. And like I said, the order doesn't matter. This is actually a dictionary, so it's working like a hash set. So it's not going to be the same order that's declared here. So first we're dealing with Blake. He's immediately no longer a free man, and he gets tentatively engaged to Sarah, which is his first preference. Then we go over and we go to Ryan. Ryan goes to ask Lizzie, and she has not been asked to the dance yet. So Ryan's no longer free, and he's immediately engaged to Lizzie. So then we go over to Josh. And Josh asks Sarah, but we see that Sarah's already taken. And when we go to Sarah, we see that Sarah is satisfied with Blake. So she remains with Blake. So Lizzie's taken. She's satisfied with Ryan, and Josh is no longer a free man. He finally gets to his third preference, which is Daniela, and they get tentatively invited to go to the dance together. And now we go to Connor. And Connor goes and asks Lizzie, but Lizzie's already with Ryan, and we know that she's satisfied with him as he's her top pick. Okay, so Sarah's also already taken in Connor's list, and finally we get to his third preference, which is Zoe, and Zoe has not been asked yet, and they tentatively accept to go to the dance together. So Connor is no longer a free man, and he's now tentatively engaged to Zoe. So at that point, all the free men are complete. The list is empty because they've all been accepted by a woman for the dance. And as you can see, Blake ends up with Sarah, Ryan with Lizzie, Josh with Daniela, and Connor with Zoe. So that is the same output that we got from the written example. And hopefully that helps you guys. And I'll go ahead and push this code up to GitHub. You can click the link in the description. And if you have any questions, feel free to leave a comment. Thank you guys for watching, and I'll see you in the next video.